Welcome back. Problem 7-15. So statement is the strut is subjected to vertical shear of 130 kilonewton. Plot the intensity of shear stress distribution acting over the cross-sectional area A and compute the resultant shear force developed in the vertical segment AB. So you can see this is the cross-section of this strut that is exerted upon by vertical shear of 130 kilonewton. So you have to find the intensity of shear stress distribution acting over the cross section, and then you have to find the resultant shear developed in this portion. Clear? So let's start with the solution. So as we know that shear stress is represented as V into Q divided by I into T. So what we will do is that we will find I for this section. So if you look at this cross section that is mentioned over here these are in millimeters, and here I have represented in meter. So its neutral axis will be at the half, because about this neutral axis it is symmetrical. So we will first find I. So I, what we will do is that we will take it, this is member 1 and this is your member 2. So I for rectangular section is 1 over 12 bh cube. So b for this is 0.50 and total height is 0.150 plus 0. Plus this will give you 0.350, and we will take the cube. Plus we will left with this portion and this portion. Clear? So it will be equal to 2 times 1 over 12 this breadth, which is this one, and height is this one, whole cube. So I will write 2 times 1 over 12 0.3 0.150 0.150 into 0.03, sorry, 0.05 whole cube. So when you solve this, you will get I will be equal to 0.1817 into 10 raised to the power minus 3 meter power 4. So this is the moment of inertia of this cross section about neutral axis. Now what we will do is that, as we have been given to find out the shear stress distribution clear over this section, so what we will do is that we will first take a point C at this point and a point D at this point. So let first take these 2 points. So if we take this, so this point is C point and this point is your D point, and we will find QC and QD. Okay, so QC and QD. So first we will find QC, and we know that QC is equal to Y dash bar into A. Now for this C portion, clear, about the neutral axis, so we will take A dash will be equal to this area, which is equal to 0.050, and this height is this one. And what will be its Y dash? So Y dash will be distance from neutral axis till mid. So this will be its Y dash. Will be Y dash, and that will be equal to 0.1 meter. How? Because you can see that the half of this will be equal to 0.075 and half of this will be 0.025, which is equal to 0.1 meter. Okay, and we will write Y dash is 0.1 and area is 0.05 into 0.150. So when you solve it, it will be 0.75 into 10 raised to the power minus 3 cubic meter. Now what about QD? So you can see that D point is this one. So QD will be for this portion. this will be the area. So we have two members, this is 2 and this is 1. So we will write Q dash is sum of y dash into area. So for first one, we will take first one is this one, first one is this one. So first one is this one. So this area is same as we have written over here, clear, plus this area. Okay, so I will write for 1 it is 0.1 y dash and area is 0.05 into 0.150 plus, now this area is how much? It is 0.05 divided by 2 is this height and breadth is 0.350. So I will write 0.05 divided by 2 will be equal to 0.025 and width is 0.350. And what will be its y2 dash. So y2 dash will be this one, distance from neutral axis till mid, and that is y2 dash, or you can also say y dash for this second portion, and that is 0.05 divided by 2 which is 0.025 meter. So I will write 0.025 as well. So again, when you solve this, you will get QD is equal to 0.859 into 10 raised to power minus 3 cubic meter. Now you have QC and QD, so you can find shear stress, which is tau is equal to VQ divided by I into T. So what we will do is that we'll find the shear stress for point C. At point C, you can see there are two thickness. One is the 0.050 and other one is this hole. So we will find for the both. So for thickness 0.05 meter, so it will be equal to shear force. So shear force is given as 130 kilonewton. So 130 into 10 raised to power 3 into Q for C is this one. This one 0.75 into 10 raised to power minus 3 divided by I is again 0.1817 into 10 raised to power minus 3 and thickness is 0.05 meter. So when you solve this, you will get shear stress is 10.7 megapascal. So this is shear stress at point C due to thickness 0.05 meter. Now what we will do is that we will find the shear stress at point C due to thickness is equal to 0.350 meter, and that will be equal to shear force, which is 130 into 10 raised to power 3. Q for C is 0.75 into 10 raised to power minus 3 divided by I is 0.1817 into 10 raised to power minus 3 and thickness is now 0.350. So when you solve this, you will get shear stress at point C due to thickness 3.50 is equal to 1.53 megapascal. Okay, now we will move to find the shear stress at this point D. So shear stress at point D will be equal to, for thickness at point D, thickness is 0.350 meter. So it will be again V, which is 130 into 10 raised to power 3, that is QD. Now QD will be this one. So 0.859 into 10 raised to power minus 3 divided by I, which is 0.1817 into 10 raised to power minus 3 into T, which is 0.350. So when you solve this, you will get value is 1.76 megapascal. So these are the stress, and now we will draw its variation over the cross section. So for that, I am going to roughly draw the section. So if you look at the side view, so this is the thickness, this portion is the thickness, clear, and this is the neutral axis. So neutral axis, this is your point C and this is your point D. So first shear stress is, you can see that thickness at this, which is 1.53 megapascal, and this is 1.76 megapascal, and this value is 10.7 megapascal. So this stress will be, first this stress will be shown over here. So this is 1.53 megapascal, and at C is 0 point, sorry, C at thickness, here the thickness is 0.05, so stress will be 10.7 megapascal. So I will join them, it will be like this one. Now you can see that the at thickness 0.035 over here, over this portion, you can see the shear stress become 1.76. So it will now come to 1.76. So at this point 1.76, and it will remain same. And below, since this is symmetrical, so this point will be also 10.7 megapascal, and it will change to 1.53. So this is the intensity of shear stress distribution over the cross section. So this is our first part. Now we will move towards second part, and in second part we have been asked to find the vertical shear force along section AB. So this is the section, this is the AB portion. So we have to find this VAB over here. So what we will do is that I have already drawn the cross section, roughly cross section over here. You can see it over here. So if we take a small area over this cross section, and this area, let this area is A dash, clear, and that is located at a distance of y from the neutral axis, and this height is, let as this is dy, clear. So what we will do is that and this height from neutral axis till top, this height you can, I will show you, this height is 0.175. This is 0.175 meter. Let me show you. You can see this is 0.15. This one is 0.15, and half of it is 0.025. So this distance from this till this, it will be equal to 0.175 meter. Okay. Now we know that this area A dash will be equal to this breadth, which is 0.050, and this height, which is equal to dy, and this dy is equal to 0.175 minus y. 0.175 minus y. So area AY A dash is equal to 0.050 into dy, and that is equal to 0.050, and dy is 0.175 minus y. This is A dash. And what will be its y dash from the neutral axis? So y dash will be this one, from neutral axis till mid of this portion. And this y dash bar, will be equal to y plus 0.175 minus y divided by 2. How? You can see that this half, the half of this will be this one, 0.175 minus y divided by 2 plus this is this value, and plus y will give you y dash. Okay, I hope you have a clear understanding. Now we know that q for this portion, for this area or this portion of, will be equal to, or for this shaded portion, q for this shaded portion about neutral axis will be equal to y dash bar into a dash, and y dash bar is y plus 0.175 minus y divided by 2. Clear? Okay, so if you further simplify this, y dash will come out to be 1 over 2 into 0.175 plus y. So I will write this value over here. This y dash will be equal to 1 over 12 into 0.175 plus y, and area is 0.050 into 0.175 minus y. If you simplify it, you will get q is equal to 0.025 into 0.030625 minus y square. Now we will find shear stress. Shear stress is equal to VQ into I into T. So V was 130 kilonewton. So I will not write 10 raised to power 3 because we will get the unit in kilonewton. And Q is 0.025 into 0.030625 minus y square divided by I, which we have calculated earlier was 0.1817 into 10 raised to power minus 3, and thickness for this area is 0.05. So when you solve this, you will get shear stress will be equal to 10951.3 minus 357.593 y square. This is the value. I will write it over here. Shear stress comes out to be 10951.3 minus 357.593.1 y square. And we are interested to find out the shear force. This is shear stress in section AB. Okay. And we know that shear force in portion AB is equal to integral of shear stress into dA. Clear? And dA is given over here. dA. This is okay. This area dA is, this is A dash. So dA will be equal to 0.05 into dy. Clear? 0.05 into dy will give you dA, or a this small difference area which is shown over here. Okay, so put the values. Integral ta is 10951.3 minus 357.593.1 y square, and dA is 0.05 into dy. And there the limit will be 0.025 meter till 0.175 meter. I will show you. You can see the limit. This is portion AB. This is portion AB. So this limit start from neutral axis. This distance is, you can see this is total is 0.025. So this is 0.025. So it start from 0.025 till this height, which is again total equal to 0.175. This plus this, sorry, half of this, which is 0.025 plus this will give you 0.175. Okay, and that will be shear force in section AB. So VAB is equal to integral of 0.025 meter to 0.175, and upon simplification it is 547.565565 minus 1789.66 y square into dy. Now it's very easy. You can take the integral of first term into dy, and then second integral of second term into dy, and you can take the limits, and at the end you will get the shear force comes out to be 50.3 kilonewton. I hope you can do this part, so that I am skipping it because it will also take time and you will able to solve it. And that was all about this lengthy problem 7.15. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about latest video. If you have any question, you can ask me in comment section. This video was recorded on the request of one of the viewer. Thank you for watching.